Okay, so welcome back to this next video in which we are discussing cosets and Lagrange's theorem. Okay, right. So in the previous video, what we discussed is the definition of the left and right cosets of some subgroup capital H under an element little a, basically. Okay. Now, something that I probably should have stressed more in the previous video is that if we are working in an abelian group, if this larger group, capital G, is an abelian group, then the left coset of H under A will actually be equal to the right coset of H under A, quite simply because if we look at the definitions here, the left coset of H under A contains all elements of the subgroup capital H left multiplied by this element little a, and the right coset of H under A contains all elements of the subgroup capital H right multiplied by this element little a. Okay, but if this is an abelian group, then A composed with H is equal to H composed with A, so that means that all the entries in this right coset of H under A will equal the entries in the left coset of H under A, so the two will be identical if we're working in an abelian group. Okay, so that's another little fact to be aware of. Okay, we'll see later on that actually there's another case where the left and right cosets can actually end up being equal to one another, and that's actually if the subgroup is a normal subgroup. Okay, so in fact you don't need the group capital G to be abelian in order for it to be the case that the left and right cosets are equal to one another. There's a weaker condition, which is that the subgroup here, capital H, is a normal subgroup. Now, of course, we know that in a abelian group, all subgroups are normal subgroups, so indeed that condition is automatically satisfied in an abelian group. Okay, so it's satisfied for all subgroups, rather, in an abelian group. Okay, right, now just before we go into that issue of the left and right cosets being the same if the subgroup capital H is a normal subgroup, let me continue on this discussion that we started in the previous video. So in the previous video we said that if little a is an element of the subgroup itself, and you construct the left or right coset of the subgroup capital H under the element little a, then you will actually just end up with the set of the subgroup itself. Okay, so these cosets will end up being equal to the set of the subgroup itself, and that's simply because the subgroup, after all, is a group in its own right, and really what we're doing there is just taking all left or right multiples of every element of the group by another element of the group. Okay, we're taking rows and columns within the group itself, and we know that a basic property that's true for all groups that in existence is that the rows and columns of the composition table for that group must contain every element of the group once and only once, and that applies for all groups, including this one that we've got here. Okay, so if you pick little a so that actually it's within the subgroup capital H, then your left and right cosets are rather boring, they're just equal to the subgroup. Now what we're going to consider is the more interesting case where little a is not an element of capital H. So let me start this on this other side. So let's say now that little a happens to not be an element of capital H. So we specifically pick a little a that is in capital G but not in capital H, so it's outside of capital H. So we're back to this situation here where little a is outside of capital H, basically. Okay, right, so what we know, going back to this picture, is that the left and right cosets then will correspond to parts of the row corresponding to A in the case of the left coset of H under A, and part of the column corresponding to A in the case of the right coset of H under A. Okay, and because of this property that I've stated now many times about the composition table of groups, which says that every row and column in a group composition table contains every element of the group once and only once, we know that all the elements, whatever they are, that appear in these left and right cosets of H under A must only appear once, basically, so you don't have any repeats in these subsections of the rows, basically. Okay, what I now want to prove is that the elements in these left and right cosets, sorry, I'll just bring that down a bit, the elements in these left and right cosets are completely distinct from the elements in the subgroup capital H. So what I want to show now, next theorem, to show that these left and right cosets of H under A, so AH and HA, are free of elements from the subgroup capital H, so are free of H elements. Okay, so you have absolutely no elements in the subgroup capital H that are in, well, you have no elements from that subgroup in these cosets, basically, if little a is not an element of capital H. Okay, so this is the next thing we want to show. That there are no elements of the subgroup capital H in these cosets if little a is outside of capital H. So again, going back to this picture, these sections of the row and column corresponding to this element A are completely free of elements from capital H, basically. No entries from capital H are in here. All of the elements that you put in here are from the group, basically. Okay, well, they're from the group, but they're from the group outside of the subgroup capital H, so they're from this portion outside of capital H. Okay, so how am I going to show that? Well, we'll do it for the left coset of H under A firstly, okay, and then we'll generalise the argument again for the right coset of H under A. Okay, so how are we going to do this? Well, once again, it's going to be a proof by contradiction, so we're going to suppose that the opposite is true. Okay, and then we're going to arrive at a contradiction. So let's say that we have some element in the left coset of H under A that actually is equal to an element in the subgroup capital H. Now, anything that is in this left coset of H under A is of the form A composed with little h for some little h is an element of capital H, basically. Okay, so here, this A composed with little h here, this is just going to represent some element of this left coset of H under A. Okay, and we are now going to say that this is going to equal some other element of the subgroup capital H. So H prime here is going to be an element of capital H, and A composed with little h is going to equal an element of the left coset of H under A. So I'm saying, okay, if we're going to assume the opposite, then there must exist some element in this left coset of H under A, which I've called A composed with little h, which is equal to some other element in the subgroup capital H, which I've called H prime. Okay, how are we going to arrive at a contradiction? Well, it's very simple. All you now have to do is take the little h here onto the other side by composing both sides with little h's inverse. Okay, so what I'm going to do is I'm going to compose on the right with little h's inverse. So on this side I'll just get little a, because when I compose little h with little h's inverse I'll get the identity back again. Okay, and a times the identity is just equal to a, so I end up just with a there. Okay, and on the other side what I'll end up with is little h prime composed with little h inverse. Okay, so now I've got little a is equal to little h prime composed with little h inverse. Now I claim that's a contradiction. Now why is that a contradiction? Well, little h here is an element of the subgroup capital H. Okay, just because that was the definition of the left coset of H under A. Okay, that means little h inverse has to be in capital H, because capital H is a subgroup. So that means that all elements of capital H, their inverses are also in capital H. So this element here, little h inverse, highlighted now in turquoise, is also an element of capital H. Little h prime, by assumption, was an element of capital H, so I'm composing one element of capital H with another element of capital H. Now, because capital H is a subgroup, when you compose any two elements of that subgroup together, you must end up with another element of the subgroup. So that implies now that little a is an element of capital H. But that's not good, because I originally assumed that I had picked little a so that it was not an element of capital H. That was my original assumption. Okay, so what I have just shown you is that if it was the case that there was some element in the left coset of H under A which was actually equal to an element in the subgroup capital H, then I can prove from that that little a was actually an element of capital H. So you did not pick little a so that it was outside of capital H. So that means that that's a blatant contradiction. So for when you pick a little a that is outside of capital H and you generate this left coset of H under A, you must end up with a set of elements that are all outside of the subgroup capital H. So they're in the group capital G, but they're outside of the subgroup capital H. Okay, right. Now to nail that in, let's modify this argument slightly to prove the same thing for the right coset of H under A. Okay, so again, what I'm going to do is assume the exact opposite and arrive at a contradiction. Okay, so I want to prove that no element of the right coset of H under A can possibly be an element of the subgroup capital H. So let's assume the exact opposite then. Let's say, okay, if it's not true, then there will be an element in this right coset of H under A which is actually equal to an element in my subgroup capital H. Okay, let's say that this element is little h composed with little a. For some little h is an element of capital H, this element is going to equal another element of capital H, which again I'll just call h prime. Okay, so all I'm saying is that if my theorem was not true, I'd be able to find some little h and some little h prime for which this was true, basically. Okay, there must exist a little h and a little h prime for which this was true. And once again, all I can do is compose on the left this time. That's the one little modification in this argument. I'll compose on the left with h's inverse. On this side I'll end up getting the identity, and therefore all I'll end up with is a on this side, and on the other side I'll get h inverse composed with h prime. And now the exact same argument works again. Okay, little h inverse is an element of capital H, little h prime is an element of capital H, that therefore implies little a is an element of H. So again, if it was the case that there was an element in the right coset of H under A which was actually equal to one of the elements from the subgroup capital H, then I can prove to you that that meant that little a was actually an element of capital H itself. Okay, so whenever you pick a little a to generate right and left cosets of some subgroup with, that is outside of the subgroup, you must end up with cosets that are completely distinct from the subgroup itself. Okay, right, so all of the elements in those cosets are distinct from the subgroup. They are elements that are in the group capital G but outside of the subgroup capital H. Okay, right, so that's now dealt with these cosets where we're using an element of little a that is outside of the subgroup capital H. Now what I want to come back to is this concept that if the subgroup is a normal subgroup of the larger group capital G, then it turns out that actually the left and right cosets of H under A end up being the same, basically, even if we're not working in an abelian group. Okay, so let's now say capital H is a normal subgroup of capital G, written like so. So you put a triangle rather than just the less than sign. So this means capital H is a normal subgroup of capital G. Okay, so let me just remind you of what the definition of a normal subgroup of a group is. Okay, so a normal subgroup is one that is stable under conjugation by an element in the larger group. So if I draw a picture of this, okay, let's have this representing our larger group here. So this is G, and then we've got our subset here, which is capital H. Okay, so we'll have capital H, the baby subgroup, here in blue. Okay, and then here in pink, this is the larger group, capital G. Okay, right. And if capital H is going to be a normal subgroup of capital G, then that means that for all little h is an element of capital H. So you pick me any element of this subgroup, capital H, okay, and pick me any element of the larger group. So for all little g is an element of the larger group, so you pick any little g is in the larger group, and this little g could be in capital H or it could be outside of capital H, any element you like. Then when you conjugate little h by little g, it has to give an element in capital H. Okay, so g inverse must be an element of capital H. It's not necessarily equal to little h itself, but whatever the answer to this is, it has to be back within the subgroup capital H. Okay, it can't end up outside of capital H. Okay, so this is the definition of a normal subgroup, and we say that the subgroup capital H is stable under conjugation by the larger group, meaning that if we take any element in the larger group and conjugate any element in the subgroup by that element, we end up with another element in the subgroup, so we end up back in the subgroup. That's why it's stable under conjugation. You don't end up outside of the subgroup. Now, in the case of an abelian group, if capital G is an abelian group, this is a completely trivial definition, because in an abelian group what you can just do is swap around H and G inverse. So you can rewrite this as G inverse H, and therefore you can cancel off the G and G inverse and get that this is just going to give little h. So in an abelian group, when you conjugate any element by any other element of the group, you just end up with that middle element back again. You end up with the little h, and little h is certainly an element of the subgroup capital H, so therefore the subgroup is certainly stable under conjugation by any element of the group. Okay, so all subgroups of an abelian group are normal subgroups. However, in a non-abelian group, this is a much more interesting concept, because GH G inverse will not necessarily equal little h in a non-abelian group. Okay, and in non-abelian groups it is not the case that all subgroups are normal subgroups. Okay, so special subgroups turn out to be normal subgroups. Okay, right. So that's the definition then of a normal subgroup. And the theorem then that we want to prove concerning normal subgroups is that if you take any little a is an element of the group, so if you take for all little a is an element of the group, okay, and you then take the left coset of our now normal subgroup under this element h, it's going to be equal to the right coset of the normal subgroup H under A. Okay, so we've already said that this is true if the larger group is abelian. We're now going a little bit further. We're saying, okay, even if we're not in an abelian group, it can still be true if the subgroup is a normal subgroup, and that will be true for all little a you pick. So you don't have to pick a special little a. You can pick whichever little a you want, basically. Okay, so what I need to show then is that all of the elements in this left coset of H under A are in the right coset of H under A, and then I need to show that all of the elements of the right coset of H under A, this set here, are in there. So I need to go both ways around. I need to take an arbitrary element in here and prove that it's in here, okay? But all that then proves is that this contains this. So I then need to go backwards. I need to say any element in here, I need to show that it's in here, and then I'll have truly shown that these two sets are equal to one another. So basically what I want to do is show that this set is a subset of this set, and also that this set is a subset of this set. And if I prove both of those things, there's only one way that can occur, okay? It's if the two of them are actually equal to each other. Okay, so we'll start off with this one here. I want to show that if I take an arbitrary element in this set, the left coset of H under A, that I can find the same element in this set, basically, the right coset of H under A. So, how am I going to do that? Well, let's start by taking an arbitrary element in that set. Okay, so we know what an arbitrary element in this set looks like. We know that it looks like the little a composed with some little h, where that little h is an element of capital H. Okay, so this is our arbitrary element from the left coset of H under A. Okay, So what do I need to do? I've got my arbitrary element now from the left coset of H under A. What I need to now prove is that that's in the right coset of H under A. So what I need to show is that there exists, okay, so fancy symbol now, there exists, let's call it a little h prime, we'll go for h prime again, okay, which is an element of capital H, such that when I multiply little h prime by A, okay, so when I take little h prime A, sorry, I've dropped the composition symbol, but hopefully you can cope with that, okay, so when I just write the two next to each other, that means composed together, okay, and I need to show that this is equal to AH, basically. So, saying this again, what does this mean? I need to find some element of the subgroup capital H, such that when I multiply it by little a, it equals little AH, basically, okay? Why? Because that will then prove that this element is in the right coset of H under A, because here, this is certainly in the right coset of H under A. So all I'm saying is I need to find an element in here that is equal to this element in here. What's the general form of something in here? Well, it's some element of capital H times little a on the right, basically. Okay, so that's all that is saying. It's saying that I need to find some element of capital H such that when I multiply it by little a, it's equal to this element that I wanted to find in the right coset of H under A. Okay, so how am I going to do this then? Okay, so I now need to give you what this little h prime is going to equal. Well, here's my advice. Try little h prime is equal to AHA inverse. Okay, now why is that an ingenious thing to do? If I put in little h prime is equal to AHA inverse, what do I get on this side? Okay, I'll put in AHA inverse times A here. So now I'm just inserting in for little h prime this, whatever this is. Okay, you in principle could work this out. I know it looks horrendously complicated, but in principle you could work whatever that is out. Okay, and I'm multiplying it now by little a here. Now what I can do is say that this A inverse and this A will cancel, okay, to give the identity, so this really does come out as being AH, which is exactly what I wanted, okay? So if I let little h prime equal this thing, then when I multiply that by A, it would work, basically. Now, what's the one last caveat that has to come up here? That element has to actually be in the subgroup capital H, doesn't it? Okay, if this was outside of the subgroup, it would be useless. Yes, it would work, but it wouldn't be in the subgroup, so we wouldn't actually have it in the right coset of H under A at all. Okay, but we assumed that capital H was a normal subgroup. So, that means that when you conjugate this element, little h here, by this element, little a, okay, which is some arbitrary element of the group, whatever that is, and I don't know what that is, but whatever that is, it has to be within capital H, otherwise capital H wouldn't be a normal subgroup. Okay, so by definition of this being a normal subgroup, that element, whatever it is, has to be in capital H. So I could take that element as my little h prime, and then I've shown you that if I do indeed multiply that by little a, it gives me the same answer as this little h left multiplied by a. So, overall, what I have just shown you then is that if you take any element, any arbitrary element in this left coset of H under A, I can find the same element in this right coset of H under A. So now what I've proven is that this has to be contained within this. So this is a subset of this. I have not yet proven that they are equal to one another, because how do you know that there aren't elements in here that are not in here? I haven't yet proven that. So what I now need to do is the other way around. I need to prove that everything in here is in here, and then I will truly have shown that the two are the same. Okay, right, so it's basically just the same argument now with a little tweak, basically. So let's go over this little argument. It will hopefully help to solidify the argument that we've just been through. Okay, so let me get this to the right level. Okay, so we want to take then an arbitrary element now in the right coset of H under A, okay, and we want to show that it will be within the left coset of H under A. So let's take an arbitrary element, and of course the arbitrary element will this time be of the form some little h composed with little a now on the right. Okay, so this is our arbitrary element of the right coset of H under A. Okay, excellent, we have our arbitrary element. Okay, now what I need to show is that this is contained within the left coset of H under A. So I need to show that there exists some little h prime is an element of capital H, such that when I left multiply it by little a, and again I'll drop the composition symbol, so such that a composed with little h prime is equal to this element that I want to find within my left coset of H under A. So it's equal to HA. Okay, so this is exactly what I need to show. I've taken my arbitrary elements in the right coset of H under A, and I need to be able to show you that that is within the left coset of H under A. Now, all things in the left coset of H under A are of the form A times some element of capital H. So all I need to show is that for some element of capital H, which I've called H prime here, that A composed with H prime is actually equal to this HA, basically. Okay, and once again, hopefully you might be able to work out what we need to set little h prime to. So here we go. Try little h prime is equal to A inverse little HA this time. Okay, and what you can do is insert that little h prime in here. The A will cancel with the A inverse, and you'll just end up with HA left over. Okay. The other thing then that we need to check is that this is actually an element of capital H. Okay, well, what have I done here? I've effectively conjugated this element, little h here, by A inverse. What I could do is I could rewrite this as A inverse H. A inverse is inverse. Little a here is the inverse of A inverse. Okay, so basically I am conjugating this little h by A inverse, the element A inverse. And because we know that our subgroup is a normal subgroup, this then is also guaranteed to be within that subgroup capital H. So although this dubiously doesn't look like a conjugate, it is, because you have to remember that little a is little A inverse's inverse. Okay, so I am conjugating just oddly, basically, by an inverse element, or an element that I've written as an inverse element. But of course this is just an element. We chose to notate it as A inverse, but there was, we were just being biased there. Okay, so although this confusingly doesn't look like it fulfills the definition of being a conjugate, think again, it is a conjugate. Okay, right, so this is an element of capital H because capital H is a normal subgroup. So that means that we can just use this element, whatever it actually turns out to be, which is some element of the subgroup capital H, and if we left multiply that element by little a, we will end up with this arbitrary element that I chose from my right coset of H under A. So what I've just shown you then is that all elements of the right coset of H under A are actually in the left coset of H under A. And now putting those two bits together, we get that the left coset of H under A is equal to the right coset of H under A if that subgroup capital H is a normal subgroup. Okay, right, so that's the more general scenario in which the left and right cosets will equal one another, okay, and that criterion of the subgroup being normal will always be satisfied in abelian groups, and of course we know that left and right cosets will always be equal to one another in abelian groups. Okay, right, so we'll call it there for this video, and in the next video we'll continue our discussion of cosets, and then we'll do a nice example.